We're on to the short answer part of Regents Review Part 6, right? This video is going to be a little bit longer just because there's 5 questions. Actually, 4 questions, but 2 of them are a little bit larger. So let's get started. Looking at the first one, right? 2 points. It wants us to solve the equation x squared plus 3x plus 11 equals 0 algebraically. Express the answer in a plus bi form. So right off the bat, I see a plus bi. That means I'm thinking this is going to have imaginary roots. And also right off the bat, right, I know whenever I'm kind of dealing with something like this, I'm going to think quadratic equation, right? I'm not going to write the entire quadratic equation down, but it is, right, we're thinking this is going to be my a, right? My a is 1, my b is 3, and my c is 11. So when I substitute it in, I'm going to say negative b plus or minus b squared minus 4ac. That's all going to be, right, the square root of 2 over a, right? When I bring this down, what am I left with? Negative 3 plus or minus. In this, I'm going to get what? 9 minus 44, which is going to give me, right, the square root of negative 35. And that's what? All over 2. Now, right, I have a negative underneath my radical, which that's going to, right, key into the fact that it's imaginary. But 35 has no real factors, right? It's a prime number. No, sorry, it's not a prime number, right? But it has nothing that I can simplify my radical down to. So all I can do from here is really just take out the I, right? Think about, I'm going to put that in red, right? When we did something like this, I would say, right, the square root of negative 35 was what? Basically just a square root of 1 times, or negative 1 times the square root of 35. So this becomes I, this stays exactly the same. So my next step, I'm just going to bring it over here, would just be to say, right, negative 3 plus or minus I radical 35 all over 2. And I think you can keep it just like this, right? You can break up and put the negative 3 over 2, but it means the same thing. If you keep it like this, your answer is correct. Moving on, right? I like this one. This is a 4.1, right? It's kind of got a lot going on here, right? First question. You have this function f of x equals 2 to the power of x. Is f of x an even function? Remember, we got to think, right, even function means it's got to be symmetrical with the y-axis. An odd function means it has kind of like that, like 180-degree rotation. So what would I do first? I'm going to graph it, right? When I graph it, easy little 2 to the power of x. I can see, right, it looks like this on my calculator. That is definitely not symmetrical, right? So if I wanted to say, right, I could say, right, no, it's definitely not an even function. Why? Because just what I said, right, it's not symmetrical. Right, symmetrical. I'm abbreviating that over the y-axis. All right, first one done, right? You could also say that if you substitute in, right, the negative x, you're not going to get same thing. It's not going to spit out the same answer if you substitute the opposite of x here. All right. Second part, right, wants us to make an equation for g of x that the function results after f of x is shifted up 5 units. Well, this is just, right, transformation of functions. If I'm shifting up or down, all I'm doing is I'm sticking a positive 5, right, because I'm going up on the end of my function. So 2 to the power of x, right, and I'm just going to erase that so it's a little cleaner, right, 2 to the power of x plus 5 is equal to g of x. Easy peasy, right? If they wanted us to shift left or right, then I would have to put it up in the exponent, but up or down is just a number by itself. Last part is tricky, right? You want to write an equation for h of x, which is the inverse of g of x. Well, inverse, right? What do you do for inverse? You have to swap the x and y values, and that's where it gets a little tricky. So, right, first step would be to turn this into a y. So I'm going to say y equals 2 of x plus 5. Second step, right, swap the x and y. So I know x equals 2 to the power of y plus 5. Now I want to solve for y, so I'd subtract 5 on both sides. That leaves me with what? X minus 5 equals 2 to the power of y. And then here it's kind of like dealer's choice, whatever you want to do to get the y down from the exponent. For me, I would just take the, the ln, right? If I take the ln, right, the natural log of x minus 5 and the natural log of 2, what's my next step going to look like? It's just going to be ln of x minus 5 equals y times ln of 2. And then I could divide, right, by ln of 2. And what is my answer? Equal, right? I'm going to say y equals, right? But really y equals turns into h of x. So h of x equals the ln of x minus 5 all over the ln of 2. This works, right? If you wanted to take, right, like log base 2 to turn that into a 1, it also works. I actually checked. There's a bunch of different ways. As long as you're consistent with what you use, whether it's the ln or like log base 10 or log base 2, you'll get full credit for it, right? So that's a good one. And 4 points, right? I think you could probably get in 2 points for the first 2 parts and 2 points for the last part. Another nice little 2-pointer, right? Same thing. I always feel like you're almost guaranteed to get something like this where you have to simplify down numbers that include imaginary numbers. For me, for this one, I don't know. I always like to just simplify, right, the I cubed first, which is going to give me a negative I, right? So if I rewrite this, right, as negative 2xi, right, because basically what did I do? I turned this into a negative I, which then made it like negative 2xi minus 3y. And then since I'm squaring that whole thing, I'm going to say negative 2xi minus 3y. From that point on, right, I'm going to FOIL, which means I'm multiplying my first term. So I'm going to get 4x squared I squared. Then I'm going to multiply my outers. So that's going to be positive 6xyi. And then another, right, inners, another positive 6xyi. And then my last one's positive 9y squared. From here, let's see, I have a couple like terms, right? These are like terms. I also can't simplify I any more than it is. I can simplify I squared. What does that become? That becomes a negative 1. So if I rewrite it now, right, negative 1 times this is just going to be negative 4x squared. I add these two together, plus 12xyi, nothing to do with the 9y squared, plus 9y squared, and I'm good to go, right? In my head, I feel like it's easier to try to simplify first, but you could also still multiply through, right? And you're going to get, you would just get up here, right, a value of like I to the power of 6, right, which is the same thing. It's negative 1, right? So it works. Last one, a 6-pointer, right? We haven't looked at a lot of these, right? So you have a population of honeybees in 2 different colonies. They're studied for 4 months. during this time, right, you have they can be basically approximated by that function p of t equals p of 0 times e to the power of rt. Um, and they're giving you two different colony kind of like growth rates, right? So if I highlight colony A, colony B, right? Write functions for both a of t and b of t. Well, all right. So, I mean, they're giving me, right, up here, my actual function I'm using, right? All I need to do is put in my unknowns, right? So I know it's going to be p of t, right? In this case, I'm going to say my green one, right, is a of t is what? What was my initial population? 10,000. The e never changes. Oops. And then what's my rate? 0.25 times t. First part done, all right? Look at my second one, right? B of t is equal to what, right? What's my initial value? 6,000 b's, still times e raised to the power of 0.45 times t, right? First part done, right? Now I'm going to use these, right? And it wants us to graph both from 0 to 4. So what am I going to do? I'm going to use my calculator, right? I'm going to put in, right, for my first one, 10,000 times e to the power of 0.25, right, with a variable, which is going to be x. Second one, 6,000 times e to the power of 0.45 x, right? This is like the oldest trick in the book, because really, like, what are you going to be doing here? You're going to be right, b of t has a smaller initial population, but it's also growing faster, so you know at a certain point it's going to overtake it, right? So if I go, right, and I'm just going to go back to my table function, right? So let me just 1 second move this down. So kind of, right, I'm gonna get rid of the functions, right? So if I'm looking at my blue function, right, which was my a of t, right? So let's see, blue function, a of t. Where did I start? I started at 0 months. I was at 10,000 Bs. At 1 month, I'm at 12,840 Bs. So, right, 12,840, it's going to be kind of like right here, right? Doesn't have to be perfect. 2 months, 16,487. So it's going to be like 1, 12, 14, 16, like let's say like right here. At 3 months, 21,000. So 21,100. So kind of like right here. And then at 4 months, 27,000. So 22, 24, 26, 27,100, right? So I have my first one, right? It almost looks linear, but it has enough of a curve, right, to make it, right, like that exponential growth. The e's in there, right? So it's got to be exponential. B of t, right, we started a lot lower at 6,000, so 246, right? And like I said, growth rate's going to be is faster, so we're going to catch up a lot quicker, right? After 1 month, I'm at what, 9,409, so we're going to get close to 10. At 2 months, we're at 14,758, so 10, 12, 14, kind of like right here. At 3, now we're at 23, so up to 20, 22, 23, right about right there. Right, so you see we're passing it, and then at 4, it really jumps up. Now we're at 36,000, so 30, 2, 3, 4, 36,000, what, 298. All right, cool, right? So you see, right, that one really does have that big woo. And of course, my line is awful because I'm on my mouse, right? But starts to jump up quicker. I graphed it, right? And then it's off your paper, right? But it wants us to stay to the nearest 10th of a month when the colonies will have the same population. So for me, I think I went into my graph and I said intersect. And when I guessed it, right, it gave me a value of 2.55 or 2.6 months. And let's see if it makes sense. 2.2, 2.3, 2.6 or 2.55. Yeah, I guess, right, like if I didn't mess up with this line, right, it would kind of be like right in the middle over here. Put that in the green. So, right, the spot where they meet would be, let's say, t equals 2.6, right? And it's also because it's saying to the nearest 10th. All right. Last one, as I go down, right, and this is taking us forever, right? But it's a 6-point question, right? So it's worth a lot. Determine algebraically how long it will take to the nearest 10th of a month for population in colony A to triple. So this case, right, we're still using that same function as before, right, for colony A, except I wanted to know when it's going to triple. So that means if I started at what, 10,000, what do I want my final answer to be? I want my final answer to be 30,000, right? So when my population gets to 30,000, right, I'm trying to find my t, right? So I'm going to basically put in, right, everything I know, which was e, and this was e to the power of 0.25. The t is what I don't know, right? If I divide by 10,000 on both sides, what am I left with? The kind of the triple rate, right? 3 times e to the power of 0.25 t. In this case, right, since we're dealing with e, the only thing I can do to take the inverse here is the natural log. You remember your little hint is, if you look at your calculator button, e and natural log are right next to each other. So these cancel out. I'm going to really quickly do what is the ln of 3. I'm bringing it over here, 1 point, I'm just going to say 0.99, right? Even though you would keep it in your calculator. What does it equal? 0.25 t. Last little step, divide by 0.25. What am I left with? T equals 4.39 or 4.4 months. Whew. And we're good to go. Hopefully that helped and didn't just make you more confused. But part 6 is in the books.